Hi everyone, welcome to our PAX talk, Understanding the Enemy, let's talk about artificial intelligence. My name is Paris, I'm a game developer at Secret Lab. We're best known for our work on Night in the Woods, and we've written like 30 books on video game design and programming and all sorts of stuff.
Hi, I'm Tim. I'm an independent game developer as well as freelance game developer. I make a bunch of little tiny games that I can't talk about due to NDA, and I also do tech writing.
Hi, I'm Mars. I'm a researcher at the University of Tasmania and CSIRO, mostly working on how to mitigate space junk, but I also do other computer science stuff.
Hi, I'm Meredith. I'm a researcher at the University of Tasmania doing educational technology. I'm also a science communicator, which just means that I talk about cool science stuff to everybody.
And behind the camera is John, who is helping us film today. He's fantastic. You can probably see his hand. Trust me, he's fantastic. And did not at all forget to bring enough microphones. That's definitely not a thing that happened. So, we are all kind of a bit of everything, and we'll get to that in a second. We are talking to you from Hobart, Tasmania, Australia, which looks a little bit like this. Specifically, right now, we're actually recording here. We're not literally there right now because we're probably talking to you on Discord while you watch this talk, but when we recorded this, we were right there. It's in a fantastic space called Enterprise, which is a co-working space in Hobart. You're welcome to come and use it if you visit Tasmania. So thanks to them for letting us use the space. Come visit Tasmania when you can. So we do all sorts of things, and this talk is kind of at the intersection of all our interests and careers. So some of us are video game developers, some of us are kind of academics, some of us are actual academics, some of us are authors, some of us are Twitch streamers, and we all kind of love playing video games and talking about video games and talking about technology. Some of us have PhDs in ICT, some of us are about to have PhDs in ICT. We do all sorts of things. So this is a representative of a diverse range of interests in the stuff that we do. So we hope you enjoy it. It's a fun thing to talk about. What's the plan? So we're going to be talking about all sorts of things. Specifically, we're going to talk about AI, artificial intelligence, and we're going to talk about a subfield of AI called machine learning and reinforcement learning. We'll talk a little bit about how video games use AI and how machine learning and reinforcement learning works in concept, and then we'll give you some demos using a video game engine to show you how it actually works. And we'll talk about how video games use or don't really use AI as it comes to be. Before we get started, I just want to acknowledge the traditional owners of the land on which we're talking to you from, the Muanina people, aka Hobart. Lutruwita. We pay respect to their elders past and present and emerging. The Tasmanian Aboriginal community is the traditional owners of this land, and sovereignty was never ceded. And we think that's really important to say. So let's get started with our talk. The plan today, we just want to tell you before we get into that, there are spider-like things in this talk. If you have a spider phobia, there will be a point or two where we tell you might want to look away. It's not too spidery, but some people get a bit scared.
So, what do most people think AI is?
That's actually a pretty interesting question. I think most people probably think of AI as things like the robots from, what was that, the Mitchells vs. the World, BB-8, or the Terminator, things like that. Yeah, Arnie. Or maybe they're thinking a little bit more friendly than perhaps some of those other examples. So, Wall-E, Eve, Big Hero 6, can't remember its name. What's the robot's name? Yeah, that robot. Yeah. Or the robot that everyone was apparently attracted to in...
Baymax. It was called Baymax.
Baymax, thank you. Or the robot that everyone was attracted to in Lost in Space. I don't know why they were all attracted to him. He looked weird to me.
Me too.
Or maybe you're thinking, from video game examples, you might maybe be thinking, the Reapers from Mass Effect, or maybe the annoying Claptrap, or maybe even things like Bastion or any of the other robots from
a bit annoying.
Overwatch. Yeah. Was a bit annoying, a bit, yeah. Or depending on, how much you like books, you might be thinking maybe a little bit more along this sort of standard where you've got, classic sci-fi novels with AI in it. And in all these sort of circumstances, the AI tends to be presented as sort of very powerful, very knowledgeable, dangerous. Or you may even be exposed to sort of AI from things like this, where you've got these stories where people, apparently fed an AI recipes, or they got it to generate, John Wick movies or whatever. The really sad thing about this is none of these are real AI.
So what is real AI then?
Well, sadly, real AI is probably less impressive. It's usually things like this. Some good examples are in our cars, in our traffic lights, in our peripherals on our computer. They're in any smart devices that you can have around your house or on your person. So if you have a smartwatch, which I just took mine off, they're often examples of real AI. So this picture here is an example of something that might be seen in like a traffic camera that is going to look at an incoming CCTV feed and be able to predict which of these things is a person or a car or a bicycle, so it can count how many people are going past or detect any dangers in traffic. It's also used by big companies on the web to try and predict things that you'll want to buy or search or watch, such as with Netflix. Every time you watch something or you rate something or one of your family members watches something, that all goes into being fed into an AI model that's then going to try and predict what things are most like what you've watched, what you're most likely to watch next. When you're searching things on Google, all these suggestions of things that you might want to search, they're not really trying to predict what you're actually going to search. They're actually giving you lots of different ideas of things that you might want to search, all of them now. They're trying to get you to search more and to think of things you might not have thought of before. And AI is also used for generative tasks, such as with this neural style transfer, when you can take an image that has some content and an image that has some style, and then combine them together to have the content of the first one and the style of the second one to make a whole new piece of artwork.
Okay, so what is AI good for then?
That's a great question. Nothing, absolutely nothing. Don't use it for anything.
Never.
Never. Don't trust it.
Just bury it in the desert and walk away.
More than the desert, the space.
Bury it in space.
Bury it in space. No. So AI, in its currently deployed uses, is best where it's designed to help a human do something. It's designed to support a human. It's designed to make our lives better. Post arty-looking photos, make better online purchases, or drive the metrics of a search company. That's what AI is best for. It should not be used to complete a whole task by itself because it makes mistakes. It doesn't really understand what it's doing. It just understands how to do something it's kind of been taught to do. So here's an example. This is a machine learning algorithm that's designed to figure out if something it's looking at is a cat. And it doesn't necessarily realize what it's looking at. Sometimes it thinks it's looking at a cat, sometimes it thinks it's looking at guacamole, I think. Sometimes it thinks it's looking at something completely different.
Guacamole cat.
And guacamole cat, yeah. If you rotate this picture of a cat slightly to the left, the machine learning algorithm that's designed to recognize cats thinks it's a picture of guacamole. And that's just because it is looking for certain elements of an image, and for whatever reason it sees the things that it most associates with guacamole in that rotated version. AI doesn't really make a lot of sense sometimes. Here's another example. This is a classifier that's designed to detect whatever's in the picture. Here we have a banana and a picture of a toaster, and it still is pretty sure that's a banana. But if we put this slightly weird, perturbed, like magic eye looking image in, it is absolutely sure that this is now a toaster.
This is clearly the most toaster image physically possible.
To a computer, this is peak toaster, right? This is like the most toaster thing that has ever existed. Yeah,
Definitely.
And that's because
it's clearly a toaster. Yeah.
And that's because this AI has been trained to recognize pictures, but it doesn't necessarily have every edge case covered because it's really hard to represent every possible state of something. Here's another great example. Is this a turtle or is this a rifle? What do you think, Tim and Meredith? Is it a rifle or a turtle?
I mean, it's definitely a rifle.
I would, yeah.
100%
I'd say handgun, yeah.
It's definitely something dangerous, whatever it is.
Definitely.
And this AI, is designed to detect pictures of something, and this is sure it's a turtle, or sure it's a rifle, not a turtle, and we can't, who are we to judge? It's a computer.
This one's very interesting because this turtle was specifically created to look like a gun to a computer. So this was essentially a project to try and not only have something that looks innocent to a human, but look like a gun to a computer. And the idea is, if you can do it one way, you can do it the other way. So you can have a gun that to a computer looks like a turtle.
Yeah.
This kind of thing is really important because when you put your luggage through the X-ray at the airport and the machine looks at your luggage, there is actually an AI in there that's designed to support what the human's doing, and it tries to draw a box around things of interest. So if it thinks it sees a gun, it'll draw a box around that gun. So the human has a look and is like, that's not a gun, that's a turtle. They shouldn't have either of those things. But if you could make a gun that looked like something harmless, then that would be a really terrible thing when it comes to that AI. So it's really important that people understand the limitations of these AIs and how when they're supporting a human, you still need the human to check what's going on. So we have another example. The general complexities of the world can just make AI really confused. Like these pictures, are they chicken or are they labradoodles or are they some other kind of dog? I can't possibly say. I love this example because if you squint and you're hungry, then it can look like chicken.
Or the other way around, if you're not hungry and you're really after companionship, chicken can look like a dog.
Yeah, if you really want a dog and you're not hungry, you're going to like, that's a dog, I just want to cuddle it. Yeah, but no, this is...
Who doesn't want to cuddle a chicken?
Who doesn't want to cuddle
right?
it? Chickens are really cute, actually, yeah.
They are.
Yeah. Yeah. Okay, so the AI can be terrible, it can be great, but it's at its best when it's supporting a human, and most of the real-world uses are supporting a human in some way.
So what has this got to do with video games then?
I mean, that's a really good question. So here we have an example of some video games. I mean, you're a Twitch streamer, you must know video games.
Yes.
So the disappointing thing, like all the AI we showed at the start, is, as a rule of thumb, video game AI is also fake. That is to say, it has nothing which academics would call AI in it, or very little in most cases. generally when you see video AI, you tend to think of things like this, such as the fantastic Skyrim, or I believe this is Oblivion actually, AI.
Yep.
Where, as we can see, they're very good at walking into walls.
Yep.
It seems real to me, Tim.
It does seem real to you. I have seen Paris walk. He does walk into walls and just
Quite often, yeah.
I play like that anyway, so it's quite interesting.
Pretty accurate, yeah. Now, so I just sort of want to go into a little bit of an example here as to, let's say, video game AI here, but I'm going to hand this over to Mars.
So to use an example that we thought most people would have heard of, we thought we would use Minecraft villages. So if you've ever played Minecraft, Minecraft is a sandbox survival game where you're spawned into a world and you have to mine resources and craft things so you can make a base and you can survive the night and there are monsters. As of the more recent versions of Minecraft, as you go about the landscape exploring this endless world, you will come across villages. And villages have villagers that live in them. And if you watch them, they look like they have kind of complex behaviors. If you just watch them for a moment, most people don't really realize that they seem like they run away from monsters and they seem like they go inside at night, but they actually have really complex behaviors. They take jobs when they live a certain amount of them in a village. If they have more houses than they have villages, they breed, and each one of them will have an employment block which they go to during the day. So if they have a farmer block, they go there and then they get a farmer outfit and they go and they do farmer activities. They stand by their crops all day. Some of them can be a cartographer, a blacksmith, a fletcher. Some of them can be it's something mean. It's called like the town idiot or something. It means unemployed. There's an unemployed version as well. And so they have these different tasks and they behave completely differently, and they can pathfind around the world, so they can not walk off cliffs and they won't jump in a pool. They always go straight to their destination, and that seems quite complex. However, it's just a bunch of rules. They actually have separate systems that check for how they navigate or how they socialize, because they stand near each other and they talk to each other or seem to mumble at each other if they go past each other. They spread gossip, where if one of them sees you do something mean, like attack another villager, when they run into another villager, they will share that information. But these are all saying, well, did you see the player do something mean? Yes, no. If you didn't, did you go near another villager who saw the player do something mean? Yes, no. Is it nighttime? Is it daytime? Is it your time to do your particular job that you picked? One of these 6 different things. And it just makes a big tree that checks all these different conditions. And for each of those sets of conditions, there is a predefined behavior that they're just following. It's not complex and it's not artificial intelligence. They're just built up of smaller, more simple systems that give you the impression of intelligence.
So what is real AI then?
Well, I mean, for the most part, real AI these days are these very fancy things called neural nets. And a neural net is, you can see one here on the screen, it's a net that's neural. That is it, thank you. No, so these are, fall into a category of machine learning is sort of the overarching group in the AI category, what it falls into. And the core idea of it is, it's sort of inspired by our own brains. Now, I've sort of like air quoted inspired there, I can actually do it, air quote, by our very own brains, because while there's definitely some similarities to how our brains work, there's also a lot of differences to how our brains work. Which of course sort of begs the question, you know, how do these things work? How does something that is a neural net, this collection of blobs of little bits all chained together, inspired by our brains, work? Well, the answer is really simple. It's lots and lots and lots of maths. And I do mean absolutely staggeringly huge amounts of maths, which we won't be looking at.
Tim is too mean to the maths.
The maths is actually kind of neat. I am a bit mean to the maths. The maths is quite interesting. There's some really cool things in there. We honestly just don't have time to sit down and be like, okay, let's talk about sigmoids. It sounds like the worst pop song ever. Let's talk about sigmoids.
We would not let Tim sing. We would cover the maths if we were doing this in person, and the crowd was like, yeah, maths. So we'll do that next year. So today, the specific type of machine learning and artificial intelligence we'll be talking about, as Tim said, is called reinforcement learning. And we can summarize reinforcement learning with this fabulous image of stonks. Reinforcement learning is the chart when it goes up. That's literally it, we're done. Reinforcement learning is when you get an agent or a thing to solve a repetitive task with only minimal guidance. That makes a lot of sense when you think about how a computer works, because a computer can do things thousands and thousands and millions of times faster than a human. So while a human can learn something eventually with minimal guidance and from trial and error, a computer can do it much, much quicker. But we're going to use a human to give you an example in a moment, just because that's how we roll. So when an agent, a thing, learns a rule set that you want it to learn through reinforcement learning, that thing is called a policy. So an agent learns a policy through reinforcement learning. A policy is actually the mapping of the inputs to the actions, which we'll get to in a bit. So let's explore this by training Meredith. We're going to train Meredith to do a relatively complicated task through trial and error without actually telling her what it is we want her to learn. And we'll reward her or penalise her accordingly with candy. We're going to make her learn a policy. We're going to know what that policy is, but she will not know what that policy is. So let's have a look at that now.
Okay, so one step forward. How are we going to... Okay. Interesting. So one step forward got me a lolly. One step forward... Sorry, got me a lolly. But... Okay. Are you sure? Okay, so back takes it away. Forward. Nice. One step forward. Hello.
Hi.
Hang on a minute. One step forward. Nice.
So Meredith seemed to get the hang of walking forward pretty quickly and did manage to associate the reward with moving forward very, very quickly. She clearly really got a lot of those coffee lollies very quickly. I'm impressed. So let's go to a slightly trickier example now. Here's a giraffe.
Okay. Okay.
Here's an elephant.
Ooh, lion. Oh. I forgot where I went. Leopard. Now there's most of the orange ones in this one. I can't remember where I put the leopard one, but I'm going to try. Yes, okay, cool. Right. Rhino, leopard. Tiger. Again, most of the orange ones, but hang on, I've got to try. Nope, apparently not. Okay. Giraffe. That was from the original one. That one? Okay, cool. Right, getting it now.
Well, that was exciting. That worked pretty well. I think Meredith did a really good job, actually.
Did she?
Well, I like to be positive. She managed to learn a policy, and by trial and error, she kind of worked out where each animal belonged, mostly. She pretty much got it. But, you know, it was a bit too complicated, really, to learn this way in any reasonably quick fashion by a human. So we're going to take a look at another example where Meredith is given the rules in advance. So instead of Meredith being rewarded or penalised for each object she's handed and whether she puts it in the correct bucket, we'll just tell her which bucket things go in advance, up ahead, before we even start.
Okay, rhino, plane, goes in C. I like this rule. Okay, leopard, jaguar, goes spot, so B. Yeah? Nice. Okay, tiger, stripes, goes in A. Cool. But that was better.
That was a lot better, or it felt better. Was it easier?
So much easier, so much.
So that really raises the question, why would you ever, do this thing with this ML stuff when you've got rules? And I mean, that's because of a very interesting thing we're going to show off. So let's try it again live with another example. Please draw a circle in the upper part of the whiteboard.
Okay. All right, so upper part, okay.
Move slightly down from the circle and slightly to the right, and then draw another circle.
Okay, there we go.
Moving slightly down and slightly to the left, draw another circle. From the first circle, draw a vertical line down towards the bottom. Below the rectangle you just drew, draw a line sloping inwards. Next to that line, draw another line sloping upwards. Connect the two lines across the bottom and connect them to the top rectangle. On the top of the oval, draw a vertical line small.
I'm actually getting the idea of what this might be. We're gone.
You have now completed your picture.
Excellent. I love it. Perfection. Right.
So that was actually really hard, or I thought it was really hard. Did you think it was hard?
Yeah, absolutely.
So the reason why you can't always use rules is just because while it's very easy to say something high level, like draw a pot plant with a small butterfly above it, it's much harder to describe every single rule to draw the nice, neat curves you need to do it line by line.
So how does the computer do it then?
Well, there are three main parts to reinforcement learning: the actions, observations, and rewards. Starting with actions, actions are what you can do. So any action you had in the example with walking backwards and forwards, the actions you could do were walking backwards or forwards, and they're anything that the agent can do to impact the environment, to action another object or to move, etc. Could be anything. Observations are what the agent knows about the world, and it is all the agent knows about the world. Unlike a human who has all these different senses, an agent that you put in a game or a machine learning scenario will only know the information you give it. It could be something that emulates human senses, like a camera for sight, or like LiDAR for depth, or something representing LiDAR. So in gaming we call them raycasts. But it can also be something more abstract, like they might know the exact position of the nearest player, or the exact position of some goal, or a flag that tells you something about the state of some other thing in the game world. And then rewards are what we give or take away, and in machine learning terms, it's usually just points. They're just numbers. They're not candy or anything fun. They're just numbers. Our agents learn that positive numbers and larger positive numbers are good, and negative numbers or lower positive numbers are bad. And so they try to optimize for the greatest rewards, the biggest number. They're just thirsting for this big number.
Number first.
Then the AI will take actions based on the observations it gets to maximize rewards. So it goes, when I observed this state of the world, and when I did this action in the past, I got a good reward. So I think that when I get this observation, I should do this action. And if we go back to our animal buckets example, the action from that scenario was take the animal you're holding, pick a bucket to put it in. The observation is what animal you're holding, or maybe even what is already in the bucket, and your rewards were giving or taking away candy.
So now that we've got the basics of how this whole AI thing works, I think we can stop being mean to Meredith and actually start doing this with proper AI now.
Be mean to a computer instead.
Always be mean to no, don't be mean to your computer.
Don't be mean to anything.
Don't be mean to anything. Good answer. So let's train an actual AI now. So to do this, we're going to use a game engine. We're going to be using a very particular game engine. We're going to be using what is called Unity. You've almost certainly played a game that is built in Unity. From memory, Unity is 70%, depending on which thing you read, might be 60% of all games made. So it's very, very popular. Here are some examples of games that are made in Unity, although there's many, many more. So what we're going to be making is we're going to be making the very advanced ball that seeks a box. Wow!
We know the session description talked about like multi-legged beasts and stuff, but we decided to go for something even more mind-blowing than that, which is a ball.
What is more mind-blowing than a ball? Nothing. It's a sphere. So let's break this down into the three individual components. So first, it's actions. It can accelerate forwards and backwards, and it can accelerate left and right. I just realized I went right and left, but you can work it out. You're all pretty smart. So what are its observations? What does it know? So it knows its current position in the world, so the XY coordinates of where it is, and it knows the box's XY coordinates of where it is on the plane. And it also knows how fast it's moving. So it needs to know that so it'll learn how to brake, because if it doesn't know how fast it's moving, it'll never work out to stop.
The ball knows many things.
The ball knows many things. Do not question the ball. The ball knows all. So we're going to give the reward to the ball when it actually hits the cube. So it's going to go boom, and then hit the cube and get a point. And in fact, we'll even then reset it and start it from scratch and make it do it all over again, caught in some sort of nightmarish land where no matter what you do, you're always chasing a cube. So for that, we're going to jump over to our handy cameraman, John.
Hi everyone, I'm John, I'm from behind the camera, and I'm going to show you the rollerball thing that we're working on. So, I've got my empty scene here, empty apart from three things: a ball, a cube, and a grid for the ball to roll on. So the ball itself is really quite simple, there's not very much to it. The main thing about it is it has this roller agent, a decision requester, and some behavior parameters. And these things are what drive the whole thing and make it use machine learning. So I'll hit the play button here, first of all, to show you this in action before we train it to try and hit the cube. So I'm using my keyboard here to roll it around. This is me piloting the ball, and when I hit the cube, it would resets. I can fall off the edge and it'll reset me there as well. Great. Cool. But this is me doing all the work and I'm very lazy. I'd like the machine to handle all the heavy lifting. So what I'm going to do is I'm going to go into my console here, and I've told it I want to start training using a specific training configuration file. I'll call this trained brain PAX 2021 and I'll hit enter, and after just a second it goes start training by pressing the play button. Great. I'll hit the play button and immediately it will start not doing super well at first because it has literally no idea what it's doing. It's only working off the actions, its observations, and the rewards. But over time, it'll start to learn to aim towards the cube. So we'll let that run for a bit. As it trains, you can see that mean reward, which is the average amount of reward it's getting over time, is going up and up and up, slowly trending towards a higher value. We can also keep an eye on this by using a tool called TensorBoard. TensorBoard is like a web page that runs inside of the training environment, and it will show me information about how my training is going. So I'll start it up. Great. I'll hop on over to here. And here it is. This chart here measures the overall reward over time, and you can see it's going up and to the right. So that's a really good sign. Cool. I think that my training is going to be done by now. So let's go take a look. I'll stop the training, and then in here is my trained brain. Cool. I'll drag it into Unity. I'll select my agent, and I'll give it the trained model that I just made. Let's hit play, and here we go. So after a few minutes of training, it knows how to roll the ball towards the cube and get its reward. It's trained entirely on this machine. It's actually pretty smart. The only information that it has is the observations that we talked about earlier. Not too bad for a little sphere.
So I was promised something far more creepy, so what about something more complex?
Well, I have this little guy for you, and this is where the spider content warning comes in, because he's got the same length articulated legs, so he kind of walks a little bit like this. It's a little bit skittery. I was told not to do the hands, so we're not going to do the hands, but he walks kind of like that, and it might freak you out if you do not like skittering. I've decided I'm going to name him Gerald, because he's cute, so come with me, Gerald. Gerald's actions are, he has 4 legs, and each of his legs has 2 axes of freedom. So he has like his hip, which we're going to pretend is my shoulder, and he can move up and down at the hip, and then he also has the, and side to side from the hip, and then he also has his knee, which is like my elbow, which can just move in and out. So between... You punched me. Between these 2 things, stop mirroring me, both of you, stop it. Trying to explain his legs. Gerald's legs can do this, so presumably he can walk, if you could imagine doing that with all 4. Stop it! Anyway, those are his actions. It's very serious. His observations are, he knows the current angle of each of his leg joints, so he has that proprioception like humans have, where even if you shut your eyes, you know where your limbs are. And he knows his current velocity in a certain direction. He knows where the goal is in the world. He knows where he is in the world, and he knows how far off the ground he is and whether he's facing the right direction. Well, not right direction. He knows which direction he's facing. So if he gets an observation that says like 90 degrees, that means he has to turn 90 degrees before he'll be facing the target. And when he faces at it, it will say 0, but he doesn't know what that 0 means, what it represents, or that there's a target in the world. And his height off the ground is because we reset him if he falls on his head. So he knows whether he's toppled, because if he learns to walk and we let him stay on his head, he'd be stuck there like a sad beetle, poor Gerald. His rewards are, he gets a big reward if he touches the goal, like the sphere. But he also gets a big penalty for falling over, so he won't just learn to like topple his way there, or he won't try to optimize for really short episode lengths by losing purposely immediately. He's also going to get a small reward for looking at the goal, which is going to speed up training to begin with, because otherwise it would take him a really long time to touch the goal by accident the first time, so he could learn that that's good. Whereas this time he's going to face it and he'll be like, oh, that's good, I guess I'll try going there first, so he only has to kind of stumble upon something that's easier to do. And he gets a small reward for moving towards the goal, which means as he gets closer, it's going to seem more obviously good. And if he turns around and walks away from it, that is obviously bad. And now let's jump to Unity.
Hi everyone, it's John again. And this is Gerald. Gerald is our little crawler walker robot. So, as you can see, Gerald has got 4 legs, all hinged at the waist, and also they've got a knee joint as well. Knee, elbow, not entirely sure which. Right now he's frozen because I've got the pause mode turned on, but let's turn that off. Hey, and away he goes. So Gerald has limited information about the world. Gerald knows where the cube is relative to his forward direction. He also knows about his own velocity towards the cube. So let's get a bit of a different view on him. There we go. Cool. Now what's fantastic about Gerald is we never did any animation for him. This behavior, this locomotion, this movement, he learned that himself entirely through reinforcement learning. We gave him information about where he was in relation to the cube, and we gave him a reward signal for achieving certain goals like turning towards the cube and moving towards the cube, and he figured out the rest himself. We didn't tell him to bend his knees to achieve speed. We didn't tell him to flick your feet in a certain way to turn. That's all emergent behavior that came out of this, and that's really, really impressive. So, Gerald.
So that seemed to work well. In fact, it worked really well. So I think the most logical thing to do as soon as you've figured out how to make something walk is, of course, to give it a gun.
No, I was going to say we make it a ball again and go back to the sphere.
No. Legs with guns. In fact, the first thing you should always do after teaching something to walk is kill. In fact, please don't ever do that. I'm serious, don't do that. So we're going to make our little robot now fire a missile. It's going to, work out how to throw it and hit.
So how does the missile actually work?
Very good question. So the way we're going to do this is to make things just a little bit simpler. We're actually going to give the missile launcher its own little mini brain. So Gerald's actually going to effectively be 2 brains working in tandem, one to walk and one to shoot.
This sounds horrifying, Tim.
It is horrifying. So the missile's actions, it's going to have 4 different actions. It's going to be able to adjust its pitch, so it's sort of up and down angle. It's going to be able to match its yaw, so it's left and right angle. It's going to be able to determine its launch velocity, so effectively how hard, if you imagine you're throwing the ball, how hard you would throw the ball. And it's going to have a specific action, which is it time for me to fire? Should I be firing my missile now, or should I wait effectively? So we're kind of giving it a trigger as well. Now, its observations are going to actually be pretty simple. It's basically just going to be given its current angle to the goal. So much like before where Gerald was given facing towards the goal, it's going to be given angle to the goal, so it knows is it facing towards the missile. Facing towards the goal rather, not the missile. And then we're going to be giving its distance, so it needs to know how far to throw things, so it's going to have to be told how far away the cube actually is. And finally, its reward structure is mostly straightforward, but there's a little bit of complexity to it. So we're going to give it an absolutely honkin' big reward if it hits the cube. If it hits the cube, mega points, good job, Gerald. But we're also going to give it a little reward for getting nearby. And the reason we do that is because otherwise you'd have to wait for hours and hours and hours and hours before it just accidentally hit the cube before it worked out that that was good. So we're going to give it a small reward for getting close and a really big reward for hitting it directly. So, back to Unity.
Like every good bot keeper, we've given it a gun. Let's see what happens when we have the rocket launcher strapped to the top of Gerald's head. So the rocket launcher, as discussed, is an entirely separate brain. The parts of the code that are in charge of making Gerald move his legs and get to the cube are entirely independent from the aiming and firing of the rocket launcher. This means that occasionally you'll see some weird behavior, like the rocket launcher will fire the rocket at a point slightly too close, causing the walker to get kicked up into the sky, which is against what it's trying to achieve, which is, kind of a nice effect. But what's cool about it is, if this was for a game, it'd be a fairly good, convincing enemy to oppose. Because a good AI is not one that wins all the time. A good AI is one that loses convincingly, and you'll notice that it's missing the shots in a fairly good and interesting way, and it looks kind of cute while it's doing it. So there you have it, Gerald with a gun. I feel safer already.
Well, that was absolutely terrifying. So, are you ready, Meredith?
For what?
Defending humankind from the robot overlords.
I mean, that's why you're here.
Why do you think we brought you?
Okay.
Okay, alright, so he's running so far.
Get power.
Wait, no one went out of here. Someone moved. Okay, alright, hang on. It's over there. Okay, alright, I still have Gerald. Close. Oh, no, it moved.
Just one.
Come on, come on, come on, come on, come on. No! 10 seconds. Here's a chance. Go.
Maybe if you hit him, you might stop him.
Yes. Suck it, robot. All right, now it's nice and close. You can get this now.
Okay.
Why don't you hit him?
Yes.
It's confused. Take that, you blow.
That was a good.
That was actually a really. Ooh. He hit it. Oh, wait. Ooh. A really impressive shot. Like, that's really hard. Him out.
Quick, hit him.
Don't
That'll
fight
stop
there.
the turn.
10 seconds. 10 seconds.
Oh no.
6, 5, 4.
No.
9 more kills. Taken out. Yes, you can still do it.
Okay, so because this is PAX, this is a gaming con, we figured we'd actually look at a real AI and in a machine learning, reinforcement learning agent in a video game context. It's a very simple video game though. It is in fact dodgeball. So we're going to look at 4x4, 4-player versus 4-player dodgeball, where all the members of both teams are robot agents that we have built using Unity ML agents. And when I say we have built, I mean we have taken these from Unity because this is a great example that Unity provides that you can actually get started with if you want to play with this. So the actions of these dodgeball playing robots are they can move up and down, left and right, they can rotate, they can throw a ball if they have one, and they can dash forward, so they can run forward really fast. There's no action for picking up a ball in the time-honored video game tradition. When one of these agents runs over a ball which they'll find in the field, it just attaches to them and then they can collect a couple of balls and throw them at their will. So those are the actions. They can move, they can rotate, and they can throw balls, and they can also move forward really fast. They also have a bunch of observations. They have a bunch of raycasts, which Mars mentioned earlier, but raycasts are basically video game terminology for a perfect laser that tells it exactly how far away from something it is. So the agents use these raycasts to see the balls, the walls, and the enemy. They know their own position, so each agent knows exactly where it is. Each agent also knows how many balls it has on it, so if it has a ball to throw, it knows that it has a ball to throw. It knows its health. It can take 2 hits before it's knocked out of the game. So basically, if it's taken 1 hit, it can take 1 more, and it knows that. It knows the position of each of its teammates. So there's 2 coloured teams, there's purple and there's blue. It knows if it's a blue agent, it knows the position of all the other blue agents. If it's a purple agent, it knows the position of all the other purple agents. And also knows the health of each of the teammates it has. So it knows how many strikes it will take to get one of its teammates out. Those are the observations. The reward's very simple. It gets a very tiny reward for hitting an enemy player with one of the balls it throws. It gets a large reward for winning the game. So if the team wins a game, the whole group gets a large reward. And it gets a bonus if it wins the game fast. So basically it has a small existential penalty. Existence is pain. The quicker it wins a game, the higher the reward it is. Those are the rewards. Pretty simple setup. Now we're going to jump to Unity and get John to demonstrate some of the ways this dodgeball game works when you have 4 robots versus 4 robots.
And here we are inside the dodgeball game. Each one of these 4 agents on each of the teams is a reinforcement learning trained agent. There's no human input here. I'm not touching the controls, I'm just sitting here talking into a microphone. And what's great is they team up, they play well together. You'll notice that they duck and evade the balls quite well. They'll know to try and pick up additional balls so they have them in reserve. They'll actually toss balls to each other sometimes. The whole thing is really cool. This thing took a couple of days to train. It is a very complicated piece of machine learning. But once the training system has begun training, you can just step away and let it figure out how to play the game well on its own. And that's astonishing. This is also useful in other kinds of games. You can use this technique for training a racing car, you can use this for training flight sims. Anything that requires continuous control can be applied to this mechanism, and it's great. But of course, it wouldn't be any fun if the robots were the only ones who got to play.
Well, that was exciting. I know exactly which sport I want to watch from now on, especially with the commentator voice from John there. That makes it all the more thrilling. But I think we can make it even more thrilling by replacing one of the agents on one of the teams with Meredith.
Oh, come on!
It's a glorious day here on the green. We're here for another exciting game of dodgeball. It's the classic rivalry we've all known, blue versus purple. The blue team is pulling a bit of a fast one this time. They've brought in a new up-and-coming champion, they say, the greatest of the great, soon to be Meredith. Meredith, how is it going?
It's dodgeball.
Ooh, that's a very interesting take. Anyway, let's get straight into the game. Can't wait to see how this goes. And they're off. It's a classic opening maneuver by the Blues. They're going out for a traditional horse maneuver attack. Purple's going in around. Oh, that was a classic hit by the newcomer. Oh, but then they're taking a bit of fire. Is that two? Wow, I have never seen it that fast. We're here on the pitch back with the cube of the match, Meredith. Meredith, how did you think it went?
Well, it was good, but it was a little bit robotic.
An interesting statement. Look forward to more from her in the future. Thank you. This is Tim from Dodgeball Central. See you next week.
So what's to learn from all this then?
Well, we've learned that AI is just learning by doing. Doing over and over and over again, really, really fast. Everyone around me is doing the little hands. I always include this GIF because this is a really fun example from Unity that demonstrates what we call emergent behavior. So you can train an AI to optimize for certain rewards, but sometimes that doesn't result in quite the behavior you're looking for. It's technically correct, but it was not what you were looking for. Like we made Gerald figure out animation for running with his even legs, if you train a biped-like form to try and teach itself to walk and reward it for locomoting forward, but you don't penalize it for overextending or using excess energy like we do in real life. We try to conserve momentum, preserve energy wherever we can because we have to eat to have energy. This bot has no concept of energy. It wants to propel itself forward as fast as possible, and it turns out that punching adds forward momentum as it runs. So usually emergent behavior is more random, less frequent, harder to observe. You might have seen it in some game AIs. But this little guy, he's an exceptionally special one. However, this can be applied to all sorts of real-world problems, like assembling a car in a factory. It might have each arm is taught to pick up something from a certain place or screw something in a certain place, being taught through those rewards to do a repetitive, specific action to play its part in an assembly line.
AI is also often used to figure out what you said. Siri is not actually intelligent. Siri is just a whole bunch of reinforcement learning and machine learning that is designed to figure out the patterns in human voice and try and actually apply those to something that Siri knows how to respond to. Same with all the other virtual assistants, Alexa, Google, etc., etc. They're all just machine learning neural nets that understand how to recognize human speech in some respect and turn that into some sort of command that they have and respond accordingly. They're not actually intelligent.
Or it's even being used in a lot of circumstances to solve some very hard problems that we know there are answers to, but it's just too complex to work out the exact process. So this here is an example of protein folding, where it's very tricky to work out how particular proteins go together. Humans can do it, but it takes us a very long time, and we're not quite sure what the magic sauce is that makes one thing fold one way or another. But if you give enough of these to an AI, it can work out this magic sauce and figure out how to fold proteins correctly.
And in the examples of recommender systems, such as Netflix, for example, recommending you things to watch, for example, you've got Amazon recommending you things to buy or read. You've just got to remember that they're doing it for their particular reasons. They're optimizing their own systems. They are prioritizing their own systems, basically. It's clickbait. It's not for your enjoyment, it's for your views. So it works for them in their own internal systems.
And in the case of video games, even when they are there just for entertainment, they're not really real AI. They tend to be just a series of rules. Rules that if you spend enough time watching them, you can probably work out what they are.
So that's our panel for you. We hope you really enjoyed it. I'm Paris. This is Tim.
Hello.
This is Mars. This is Meredith. And we've also got John, who's been diligently operating Unity and our cameras and our microphones. And he's coming in here.
What?
Thank you, John. We really hope you enjoyed our little session for you. Check out Meredith on Twitch. She's doing amazing stuff. And hopefully we'll see you in person in Melbourne drinking coffee that's not quite as good as Hobart's coffee.
It's not as good.
Next year. Thank you. Please chat to us in the chat. And Mars would like you to talk to her about Deathloop in the Discord. Not about AI, apparently.
Nobody will talk to me about how great this game is.
Thank you, Mars. Thanks, everyone.
Thank you.